So now that we've talked about how the device behaves as we apply a forward and a reverse bias, and we had this ideal diode equation, we're ready to come and look at it sort of holistically and define sort of our basic operation of what we're going to call our PN junction diode. So I've copied from our previous video our ideal diode equation here. And so ultimately what we're going to see is that this device has nonlinear behavior, again because we have this exponential term. And we're going to see it has a rectifying IV relationship. And so what does that mean, rectifying? What that means is that it only is going to conduct in one direction. So only conducts in one direction. Okay, so let's just sort of sketch out what our current is going to look like as a function of our voltage. And so I'm just going to put some typical values. Of course, this is going to change a little bit depending on a particular diode, but let's plot our VD in volts down here, and let's plot our diode current ID in milliamps up here. And so for maybe sort of a standard electronics diode, so something with relatively small voltage and current, let's say we're going up to a scale of maybe about, say we're 1, 2, 3, 4, 5 milliamps. So we're on sort of single digit milliamps. For certain applications, of course, we could have much higher current, even in the amperage range. And then let's say, just to get sort of a rough reference, let's say we have 1 volt here for our diode bias. And so this V sub D is going to be our forward bias case. All right, so looking at this ideal diode equation, what we can see is that if this VD voltage up here is negative, then this -1 term here is going to dominate, and our I sub D is essentially just going to be negative I sub S. But remember, our I sub S is a very small value, so we said it's anywhere from 10 to the minus 18 to 10 to the minus 12, so typically very small for PN junction diodes. So what we're going to have then is we're looking at this case over here for VD less than 0, and so we can draw our current here at some very small value. And so I'm actually exaggerating a little bit. Of course, that would be even closer to that axis, but just so we can see, I've put it very small there. And so let's come here and label this. This is ID equals negative IS. All right, so now in our other case, what we need to keep in mind is, of course, the value of this VT. So remember, our VT at room temperature is about 26 millivolts. And so what that means is we're going to see this exponential really start to kick in once our VD begins getting larger than that, significantly larger. So for instance, again, we're assuming that this coefficient constant n is just equal to 1 because we've not been told otherwise. And so what that means is we have just VD over VT. So let's say that VD is equal to VT. So then, of course, we're just going to have e to the power of 1 minus 1, so we don't really have appreciable current. But as that VD gets much larger than 26 millivolts, we're going to see significant current increasing, of course, exponentially. So if we come down here and just do sort of a rough sketch, we can say initially we have sort of a small amount of current, and then it's going to be increasing exponentially, and we'll get a curve that looks something like this. So we have this exponential increase here. And one thing to note as well, so here is an exponential increase. Oftentimes you'll see these on semi-log plots. So if we have a semi-log plot, typically our current is on a log scale, and in that case you'll see a linear curve. Again, just a common way to represent that. And so if we relate this back to our previous two videos, we can sort of break this down into our two regions. We can say over here on the right side where our VD is positive, this is our forward bias case. And over here on the left side of 0, this is our reverse bias case. And so that's kind of how we can relate that to what we talked about previously. Okay, so let's look at sort of just a simplified diagram. So we've already kind of seen this before, but sort of typically we don't necessarily need to draw in that depletion region in the middle, but we can say here we have just our P and our N region. And if we have some applied bias across it, V sub D, we're going to have some current I sub D going through our diode. So we could call this just our simplified diagram. But of course, even that's a little too complicated to put in a circuit typically. So usually what we're going to do if we have our diodes in the circuit is we have sort of this little triangle with a line on one end. Let me see if I can't draw this decently. And then we have our connections coming out of that. And so we have a plus minus VD across that, the same as we did above. And we have a current I sub D going through it, just like we had above as well. So this is the actual circuit symbol that we're going to use whenever we have diodes in the circuit. And this is again for a p-n junction diode. We'll have slightly different symbols if we have slightly different diodes. And again, we're going to talk about that a little later on. One thing I forgot to mention in a previous video as well that I want to make sure to touch on at least a little bit is if we're looking in this forward bias case here, once we get into that exponential behavior, for VD large enough, this -1 term becomes negligible. So as you're doing calculations, that can help you simplify a little bit. Okay, so there's our circuit symbol for our p-n junction diode. What do these diodes actually look like if we go to pick them up in a lab? So oftentimes what they're going to look like is they're going to be cylindrical. So let's see if I can draw this decently here. So we have something that looks like this. And then on one end, we're going to have sort of a shaded in strip around our cylinder. And so what that represents is this is going to be our P side, and this little strip here indicates our N side of the device. And so that can help you orient it because of course this device won't carry current in the same direction. So it doesn't operate the same if it's placed in sort of backwards versus forwards. So we want to make sure we have it oriented appropriately. So in the following videos, what we're going to do is we're going to talk about some considerations, particularly related to this IV curve. Then we're going to talk about how to analyze some simple diode circuits. And then finally, we're going to talk about other simple types of diodes.